Let's draw the Lewis structure and determine the VSEPR geometry of phosphorus pentachloride. Let's start with counting up the valence electrons. Phosphorus is in group 15 and has 5 valence electrons. Chlorine is in group 17 and has 7 valence electrons, and there are 5 of them. Let's add them up. And we have 40 valence electrons to draw this Lewis structure with. Phosphorus, let's put him in the middle because it's less electronegative than chlorine. We'll surround phosphorus with the 5 chlorines. Next, we need to connect the terminal atoms to the central atom. That's called the bonding pair. Each of those bonding pairs is 2 shared electrons, so we're down to 30 valence electrons. Next, let's get the terminal chlorines and octet. Each of them already has 2 in the bonding pair with phosphorus, so they each want 6 more to achieve the octet. That's going to use up the remaining 30 valence electrons. If you check out the formal charge, the formal charges are all 0. The formal charge is the charge of an atom in each of the atoms in the molecule. And so we can calculate that by taking the number of valence electrons in the neutral atom, subtracting the number of dots, which represent the non-bonding electrons, and subtracting the number of lines, which represent each atom's share of electrons in the covalent bond. So do that, they'll all be 0. So this is your Lewis structure for phosphorus pentachloride. Finally, let's check out the VSEPR molecular geometry. The central atom here is phosphorus. It has 5 regions of electron density. When you have 5 regions of electron density, by the way, phosphorus can have more than 8. It's an exception to the octet rule because it has access to d orbitals. It's a 3rd period element, so they can oftentimes have what's called an expanded octet. Alright, when you have 5 regions of electron density and there are no lone pairs, in other words, they're all bonded to other atoms, then the molecular shape is trigonal bipyramidal. It's 2 triangular pyramids that share the same base. Alright, so you need to know the bond angles are 90 degrees and 120 degrees. I'm going to redraw this using the line dash wedge a little bit bigger, and I'll point out those angles for you. So phosphorus is central, and we'll put one of the chlorines on the vertical axis. It's on the same plane of the screen. Another one also on the same plane of the screen, and a 3rd one also on the same plane of the screen. In other words, these are all right angles. They're 90-degree angles. Now these last 2 are going to not be on the same plane of the screen. This one's coming out of the screen in front of you, and this one's going behind the screen. Do that a little better. Alright, so I'll put the angles in again. All of the, well, let's do these 3 equatorial chlorines along the equator of this model, if you will, are 120 degrees apart from each other. That's the maximum they can get in terms of separation along that plane. Now these are all 3 of those are perpendicular to the axial chlorines, the ones on the north and south pole, if you will. All right, I didn't draw the valence electrons for each of these chlorines because that will clutter up the screen, and the point of this is to show you the bond angles. So once again, this is known as trigonal bipyramidal. All right, here's your triangle base, and they all meet at that pyramid top, and that same base also meets at the bottom. So it's 2 pyramids with a triangular base that they share.